Having studied about qubits and the gates that we can perform on the qubits, we are now ready to study a quantum algorithm. Now, algorithm is basically a sequence of steps or instructions that are carefully designed to answer a particular question or to solve a certain computation task. The algorithm that we will study now is proposed by David Deutsch in the year of 1985, called the Deutsch's algorithm. Before we look at the algorithm, let me ask you the following question. Suppose I give you a function that takes a single bit as the input, it could be 0 or 1, and give the output which is also either 0 or 1. We have already seen that there are 4 types of such functions, which I reproduce here for your reference. There is the constant type, which always gives you the same output, or there is the balanced type, which gives you different output. So here, the term balanced means each of the 2 output occurs with the same proportion. So here, the 0 will appear and the 1 will appear, and here, the same for the 4th function. And they appear with the same proportion, so it's called a balanced function. The question is basically quite easy. Suppose I promise you I have given you one of these 4 functions here, so it's either the type of the constant or the type of the balanced. Are you able to determine whether this function is constant or balanced? Well, you say that the answer is actually quite easy. I just have to put in the input of 0, check what is the output, and I put in the input as 1 and check what is the output. Then I'm going to compare these 2 values. If they are the same, then this is the constant function. If they are different, that's a balanced function. That's true. However, you see that what you need to do is that you need to evaluate this function twice. Can we do better than that? Is it possible to evaluate the function only once in order to tell whether this function is constant or balanced? If you spend a little thought on that, this is not possible because you have to compare the 2 values. However, let's see what we can do with quantum computing. Before we go into that, let me first imagine that a certain machine is used to evaluate the function. You can think of it as a calculator or a computer that we do not have to worry about the inner working now. So basically the machine is used to help us to find the value of the function. The function can actually be quite complicated, although this looks quite easy. So we do not worry about the inner working of that first and just treat it as a machine. Classically, we have to query this machine twice. So that is to say that you put in 0 and the machine gives you an output, and you put in 1 and the machine gives you another output, and you compare these 2 values. However, we will see that if this machine is a quantum machine, it is actually possible that we only query this machine once and we will find the answer to this question in a deterministic way. That is, we will know for sure whether this function is balanced or it is constant by inquiring this machine only once instead of twice. It's quite magical, isn't it? To see how it works, there are 2 things we need to understand now. One is quantum parallelism, and the other is about an effect called interference. And I will explain both in the next part. Quantum parallelism is one of the fundamental features in many of the quantum algorithms, generally speaking, but at the risk of oversimplifying, it allows this quantum machine to evaluate the function for both input simultaneously. However, such statement sometimes can be misleading because what is happening is more subtle than that. So let me explain further on what is happening in more details. For that, let's now look at this black box. Previously, I've just generalized this as a machine. So this box is trying to evaluate the function that we would like to evaluate. And for now, let's not worry about the inner working first, as we said. Let's just treat it as a black box. In many quantum computing tasks, such a black box is called an oracle. So what the oracle does is that by the appropriate choice of the sequences of gates inside, it is used to evaluate the function f of x. So for example here, this UF transforms the state x, y, which is just another notation for the tensor product between the x and the y, there's two qubits, into x and y plus f of x modulo 2. Let's see what is happening here by making specific values of the inputs. Let me always initialize the y as 0. So after this black box or after this oracle, what we will get is x. And since y is equals to 0, we get f of x. So effectively, what this black box is doing for us is to evaluate the function of x. And by measuring the second qubit, we will know the value of the f of x. As we said before, classically we have to run through this black box twice. Well, that is because, let's say if I would like to have the value of the function at 0, what I can do is to put the state 0 for the input x. Then the output at here will be 0 and f of 0. I could also certainly initialize the state into 1 rather than 0. So let's say I'm going to initialize as 1. So pretend you don't see the 0. So the state is just 1. Then what I'll get over here is 1 and f of 1. I guess you already know where I'm heading to, because we all know that in quantum mechanics, it is possible to have the qubit in a superposition of the 0 and 1. So what I can do is adding a Hadamard gate before the qubit enters this black box. So now the state becomes 0 plus 1 over root 2, a superposition of the state 0 and 1, and after running through this box, what we will get is a superposition of these two states. Now, let's look at this state very carefully. Something quite remarkable is happening. There is the first term, which contains the information about f of 0. In the second term, there is the information about f of 1. It is as if the quantum computer is evaluating this function at these two different inputs simultaneously. However, this information is not immediately useful. Why is that so? Because we still have to do a measurement in order to reveal the information. And looking at this state, if a measurement is done over here, the first qubit could either be 0 or 1. If the first qubit is measured to be 0, we get the information about the f of 0. If the first qubit is measured to be 1, and then by measuring the second qubit, we can get the information about f of 1. However, looking at this state, we see that this measurement on the first qubit is probabilistic. Half of the time, its result is 0, half of the time the result is 1, but a single shot measurement, that is, if we only query this machine once, we could get either the 0, then we have the information about the f of 0, or only the 1, then we get the information about the f of 1, but not both of them. So while this information is clearly in this state, it's not immediately useful. We need something more than just parallelism alone. For example, there might be something that we have to do over here before we send in the state for the qubit y. We have to design the state preparation more smartly, or for the measurement, maybe we cannot do a projective measurement at a computational basis here to reveal the information. We might also need to do something over here before we do the measurement. Or maybe here as well. So in the next part, we are going to see how to design this algorithm with the appropriate choices for the gates over here in order to extract the information contained over here. And for that, there is an effect we are going to make use of, which is called the interference, and I will explain next. Before I explain the role of interference in the Deutsch algorithm, let me mention that interference is actually quite common in everyday life. You should have already seen that, suppose you have a water tank, and you have two dippers that are dipping and produce two circular waves. As the waves propagate to the far ends of the water tank, you will see an interference pattern. That is, there are certain places you have a very high crest, and there are certain places you have minimum disturbance. This is because we know that when the waves meet each other, when the crest meets the crest, the amplitude gets even higher. When the crest meets the trough, this cancels out. So these are called the constructive interference and the destructive interference. To illuminate more on what is the origin of the interference, let me explain a quite famous experiment called the Young's double slit experiment. So let me show you what happens in this experiment. In this experiment, there are two slits where a quantum particle from above could pass through either of the two slits and arrive at a screen which is quite far away from the slits. So these are not drawn to proportion, but the screen should be quite far away from the slits. This experiment has been done with water waves, with photons, with electrons, etc. And we always observe an interference pattern at the screen. That is, at the screen, you will see some pattern which look like this, where the intensity oscillates between high intensity and low intensity. What is happening here? We know that we can describe a quantum particle by the probability amplitude, so there is a certain probability amplitude that the quantum particle could pass through the first slit and arrive at a certain position on the screen. Let me just assume it's over here. However, the particle could also pass through the second slit and arrive at this same position on the screen. We associate each of these two paths by a probability amplitude, let me call it alpha 1, and another probability amplitude alpha 2. So the combined probability amplitude is alpha 1 plus alpha 2. In order to find what is the probability of the particle arriving over here, we need the absolute value squared of this. Remembering that the alpha 1 and alpha 2 are complex numbers, so the alpha 1 could be written as x1 e to the power of I phi 1. Alpha 2 could be written as x2 e to the power of I phi 2. So here x1, x2, phi 1, phi 2 are all real numbers. Working this expression out, this is just a matter of high school math, and you will see you get x1 squared plus x2 squared plus twice of x1, x2 cosine of phi, where the phi is the difference between these two phases, phi 2 and phi 1. So this is a relative phase. And because of this term, this cosine phi, which oscillates, and this gives rise to the interference effect. That is why, depending on what value of phi, which is the relative phase difference between these two phases, you will start to see oscillatory patterns over here at the screen. There is another interference effect, which is also quite interesting, and that's called the two-path interferometer. So suppose this is a 50-50 beam splitter, which can be realized by a half-transparent mirror, and when the photon comes in, there is a chance of 50% that it is transmitted. There is also a 50% chance that it is reflected. After that, let's put a mirror here to redirect the path over here, and also put another mirror to redirect the path over here. To see interference effect, let's put another 50-50 beam splitter over here, and put two detectors, one here, so let me call it detector 1, and another detector 2 over here. If you do this experiment and observe what is the probability that the detector 1 click, you will see that depending on the difference between the phase of this path and this path, so one of the paths could be slightly longer, or there could be certain optical elements added into one of the paths. So there is a phase difference between these two paths. And due to this phase difference, the probability again shown an oscillatory pattern. So depending on the phase of the phi, this probability could go between 0 and 1. Again, an interference effect. Here, something is quite remarkable. That is, if you have chosen this phase carefully, then the particle could emerge in one of these two paths with certainty. That is, probability equals to 1. This is actually quite remarkable because we know that in quantum mechanics, measurement always gives probabilistic outcomes. However, making use of the constructive interference, it is certain that only one of the detector will click, the other one will never click if the phi is a certain appropriate choice of the value. Let us now look at a final example, which is more closely related to what we have studied so far in the circuit model of quantum computation. That is, let me prepare an incoming state, which is 1 over square root of 2, 0, plus e to the power of I phi 1, 1. We can prepare this state by initializing in the 0 and apply certain unitary on it. Now, after this preparation, I'm going to do a measurement on this state. However, the measurement is not done in a computational basis, and that's very boring. The measurement is done in another basis. So let me first write down the basis. Mathematically, the measurement is described by these two projectors, pi 1 and pi 2. Where the psi 1 So the psi 1 and psi 2 are given by these two expressions, and you can see that relative to the in, they look very similar, except there's a difference of phi 1 here and phi 2 over here. So this measurement is effectively by doing a unitary before the measurement. So we've talked about that we can realize a measurement in other bases in this way. Let's find out what will happen. So this measurement will give us two outcomes. One of these two detectors will click. There's the probability P1 that corresponds to the detector pi 1 will click. So let me call it P1. And there is a probability P2 that the detector corresponding to pi 2 will click. Let's find out what is the probability for P1. So we've learned that P1 is given by the trace of this measurement operator, this projector pi 1 with the state rho, which is the cat in with the bra in. By now, I believe you are able to carry out this computation and be able to show that this probability is given by 1 plus cosine of phi over 2. Where the phi is again a relative phase between the phi 1 here and phi 2 over here. Let's see what is happening over here. First of all, you notice that oscillatory pattern. So this probability oscillates depending on the value of phi. For certain values, if the phi is equal to 0, that means these two phases are the same. So for simplicity, let's say phi 1 is 0, and that means phi 2 is also 0. So here, this is the plus state, and this is also the plus state. And that's of course true, because if your incoming state is plus and your measurement is done in the plus-minus basis, the P1 is always equal to 1, so the detector here, corresponding to the plus state, will always click. However, if this phase difference is pi, so cosine of pi equals to -1, so here you get 0, so that means this detector will never click, and P2 will be equal to 1. And you see that this is because when this is 0 and when the phi 2 is pi, this is e to the power I pi, which is -1. So here you have a state 0 -1, here you have a state of 0 +1. These two are orthogonal states, and of course, that means this detector corresponds to the pi 1 will never click. While we notice this interference pattern again, that is due to the relative phase, something also quite remarkable is here that you see for certain choice of the phi, one of the detectors will click with certainty and give us deterministic results. Here we can see the reason rather clearly, the constructive and destructive interference, because the state is simple and there's nothing much happening over here. For a more complicated algorithm, so there is the state preparation, there are many gates in between, and finally there's a measurement. Although there is more complicated things happening in between, but the underlying principle is about the same. Basically, by smart choice of the initial state, by smart choice of the gates and the sequences, and by smart choice of the measurement, we make use of the constructive interference effect to make sure one of the detector will click with certainty, and that will give us the deterministic answer to the quantum computational task. We will see how that works out in the Deutsch algorithm. Before we walk through the algorithm, let me make a final remark about the black box. Previously, we mentioned that we do not have to care about the inner working of the black box and assume it is functioning. However, if you are feeling uneasy or puzzled about this black box, let me open it up for you to see the inner working. 4 possible black boxes are actually shown here, with 2 of them already quite familiar to us when we were discussing about the C0 gate. In fact, we mentioned that the C0 gate, or the C0 gate with a second X operator on the second qubit, can be used to evaluate the function of the balanced type. If you spend a little thought over here, you can convince yourself that this construction of the black box can be used for the evaluation of the function of the constant type. So we know that the constant type function, for example, f of x equals to 0, it does not depend on the input x. Hence, for example, that's why you see over here there's no entangling gate between the 2 qubits. Whether the x is 0 or 1, it does not affect the value of the function fx. So the construction of the black box over here can be used for the function of the constant type or balanced type. It is just that we do not know which one is inside, and our task is to find out which one. The algorithm makes use of parallelism and interference effect that we discussed so far. The Hadamard gate helps us to prepare a state in a superposition of 0 and 1, and we said that alone is not enough. So in fact, we need also a Hadamard gate over here, as well as another Hadamard gate before the measurement, in order to review the information contained in the state. And now we will show how does this work. Now, let us walk through the algorithm. At first, the state is 0 and 1, and each of them is being applied by a Hadamard. So at this stage, the state goes from 0, 1 to plus minus. Let me write out this in a computational basis. This is what I will need later. So I have 1 over root 2, 0 plus 1, tensor with 1 over root 2, 0 minus 1. So there will be a term that goes with 0 tensor with this minus ket, and there's a term that goes with 1 tensor with the minus ket. So let me study each of them separately. So in general, I have a term which is x, that is tensored with the minus ket. The x could be 0 or 1. And let us study the action of UF on this state. So the UF x on x of 0, turn it into, according to this equation over here, the first x is unchanged. For the second one, we have y, which is 0, plus f of x. So we will have f of x. And when the UF is acting on x with the 1, again, the x is unchanged. But here we have y, which is 1, so it becomes 1 plus f of x. Okay, here I have been sometimes written down this expression without the tensor product or with the tensor product, or sometimes just write inside the cat. All of them are referring to the same thing. So now, since the UF x on x of 0 give us this, x on x of 1 give us this, but now have a superposition of them. So what we get at the end, the x is always the same. So let me write it in front. Being tensored with the 0 turns into f of x. The 1 turns into 1 plus x over root 2. Now, let me remark, the value for f of x and the value for 1 plus f of x, they always differ by 1, right? Doesn't matter what is the value of f of x. So these two values always differ by 1. So to see in more details, you can see that if f of x is equals to 0, then what you have over here is 0 minus 1. If f of x equals to 1, then here you have 1 minus 0, okay? So in the first, so maybe let me write it down. In the first case, you will have 0 cat minus the 1 cat, okay, with this coefficient and this one, but I'm only writing down this part. If f of x equals to 1, then this part is 1 minus 0, which is the negative of that. So this is negative of 0 minus 1. So it does not matter what is the value of f of x. This part is always 0 minus 1, but with a plus minus 1 in front. So I can write this more compactly as minus 1 to the power of f of x with the rest, which is the x tensor with the 0 minus 1. So you can convince yourself that because this part is always 0 minus 1 over square root of 2 with the x, if f of x is 0, so minus 1 to the power of 0 is positive, so that's why we have that. If f of x is 1, then minus 1 to the power of 1 is negative 1, so we pick up this negative sign. So this expression over here with this condition can be compactly written in this way. Alright, with that, now we are able to find out the state over here. So let us continue. So now I'm going to write down the state after this black box because I've already evaluated what is the action of the UF on this state. So after the UF is being applied, let me give it a name. So at this stage, okay, let me call this state just psi. So for the 0 cat, okay, for the x is equal to 0, we will have minus 1 to the power of f of 0 times 0 cat tensor with that. Now I will just shorten the notation to call this the minus cat. Okay, I need a square root of 2 over here. That's the first part. And there's also the second part that goes with the 1. So when x is equal to 1, I have minus 1 to the power of f of 1 with the 1 cat tensor with again the minus cat over square root of 2. Okay, so what you see over here is that the second qubit is always in the same state minus with tensored with something in front, so that means this can be written as a tensor product of the first qubit with the second qubit, where the second qubit is always minus. Tensor, let's write down the first qubit. So the first qubit is 1 over root 2, and there is the 0 ket goes with this coefficient, there's the 1 ket that goes with this coefficient, so we have minus 1 to the power of f of 0 with the 0 ket plus the minus 1 to the power of f of 1 with the 1 ket. This is the state of the first qubit. Okay, so this is the state of the first qubit, and this is the state of the second qubit. So this is the state after it emerges after this black box. Now, let's look at this state carefully. We are promised with the fact that the function is either balanced or constant, so that means there are only two possibilities. The first possibility is that the function is constant, so they have the same value. So that means here, this coefficient in front of the 0 is the same. Either both are -1 or both are 1. So if both f of 0 and f of 1 equals to 0, then this is +1, this is +1. Or if both are 1, then this is -1, this is also -1. So in either case, as long as the function is balanced, here we always have the ket 0 plus 1 up to a plus-minus overall sign outside. So that is to say that the state will then be 1 over root 2 up to a plus-minus in front of the 0 plus 1 for the first qubit, and for the second qubit is minus. And for the second case that the function is balanced, that means they take different values. So one of these two terms will be plus and one of the two terms will be minus. So that means you either get 0 minus 1 or 1 minus 0. So in either case it's equal to 0 minus 1 up to a plus minus in front. So we can write the state as plus minus 1 over root 2, and inside we'll have 0 ket minus 1 ket tensor with the minus ket. By now you can already see that these two states are orthogonal, because this is basically the plus state. The overall sign of plus minus 1 is a global phase factor in front, which is not relevant, and this is a minus state. So you can already see that this state and this state are orthogonal, and they can be perfectly distinguished by a certain measurement. Hence, with the action of this Hadamard over here, acting on the first qubit, this state is turned into the 0. I have ignored this global phase of plus minus 1 in front. And if this is true, then the minus will be turned into the 1 state with the Hadamard. So, a measurement in a computational basis on the first qubit, let me denote the probability that the detector corresponds to the 0 state will click as P0, and the probability that corresponds to the 1 state will click as P1. In the first case, where the function is a constant, we will see that P0 is equal to 1. So this detector click with certainty. In the second case, where the function is balanced, we have 1, so this P1 will be equal to 1. Hence, by looking at which of these two detectors will click, we can tell for certain whether this function is of the type of constant or is the balanced type. Now, a remark is in order. Here, it is important to realize that effectively what we are calculating or what we are computing is the sum of the function evaluated at 0 and 1, and where the sum is modulo 2. So in the first case, if they are constant, either both are 0 or both 1, this sum is equals to 0. If they are balanced, then this sum is equal to 1. So what we're getting here is a global property of the function. So we only know the sum of f of 0 plus f of 1, but with no access to the information about what is the value of f of 0 and what is the value of f of 1. So that is why previously I said when we say with quantum computers we're evaluating the function with both input values simultaneously, and that could be a somewhat misleading statement, and we have to be careful with that. One more remark about the difference between classical parallelism and quantum parallelism is that in the classical case, what we need to do in order to find out the question to this answer, is it balanced or is it constant, is we either have to increase our time, that is, we evaluate the function with the input of 0, we evaluate the function with input of 1, or we can also do that with more resources. So for example, you can have two copies of this machine. One of the copy is used to evaluate f of 0, the other copy of the machine is used to evaluate f of 1. So you see we need an increase either in the time or in the resource in the case of classical parallelism. There is something fundamentally different in the case of quantum parallelism, where in this case we make use of the quantum property. That is, we use the effect of superposition as well as interference so that the right answer will emerge with certainty. In fact, the Deutsch algorithm is the very first quantum algorithm that has shown quantum advantage. It is a simpler version of a more general algorithm that is called the Deutsch-Josa algorithm. There, we can find an exponential speedup when using quantum algorithm as compared to classical algorithm.